So. Let me introduce my lathe. I usually just call it the lathe, or sometimes I actually call it Turner, like in Tina Turner. It started its life in China some 20 years ago, and it have had a pretty rough life out in the cold in my garage. After a rehab period where it got cleaned up and the rust was removed and all the bearings in the gearbox were replaced, it now lives happily here indoors. Right now there is a 3-yaw 100mm shock on it, but I have also a 4-yaw shock and also a larger shock which is 160mm. It can take workpieces up to 200mm, and then it starts to interfere with the slideways here. And it can also interfere there, as it has already done. But I guess we are mostly interested in the CNC part of this, so let's have a look at that. So the axis control is via this ball screw here, that is a 16mm ball screw, and a ball screw in here, and I think I had to go down to 12mm there because it's really cramped with place there. The X-axis stepper motor is mounted in here. It is not very much space there. It could perhaps have been better to mount it on the rear side over there, where it is more space, but well, now it sits here. The axis is driven by the belt here that gives some extra torque for the ball screw. And the Z-axis stepper motor is here. It's a NEMA 23 motor. It seems to be a little bit longer than 100mm, and it's usually strong enough for most operations except for drilling large holes. I use Linux CNC on this system, and here is the display I have for that. And I use a touchscreen here, so jog back and forth, and the other way I control it, that is via this gamepad. These buttons here, they always give me a certain speed, so it's 0 or nothing, but if I press that one and use this one, I can actually have some control over the speed. This one actually works pretty good. I have become used to use it, and I prefer this one very much in the lathe. So I use this one in the milling machine, and there that works fine, but here it is so awkward to switch to X, to switch to Z, and then slowly get in there. And I don't need that precision here, really. I have other ways to get the precision. So let's have a look here how I usually use Turner. This is a G-code program here, and there are lots of fine cuts here to shape a certain profile. There you can see the profile to the left. So that is an automatic way, and well, no problems with that. I want of course to be able to use the lathe in a manual way, and then I use this one typically. Here are a number of different operations here. So this is a turning operation where I specify the end SZ and the diameter I want to go, and the feed parameters, and just cut away, and that is extremely convenient. So here is where I get the precision from those settings there, and that is turning inside a boring, facing to make a small radius, have chamfering, and doing threads is here one, drilling and tapping, that is for synchronized tapping, and for plunging for grooves or parting, and that works very nice. To get this to work properly, I have to have the diameter set up properly, and also the Z. And when I do this manually, I only work here with the coordinate system offset. So as you say, I make a test cut and measure how big it is, and I enter, well, it became 52, and oops, sorry, no, this should be okay. 52, and then it is on 52. the same for Z position. So that's an easy way to get good precision. So if you look here on the drive side here, so here is the motor for the spindle, and during the rehab period I replaced that small motor that was within. This one is a 2 horsepower motor that drives via a tooth belt. That works nice. And there is a VHD that lets me control the speed. So it's a 50 Hz motor, but I go up to 70 or 80 Hz here. So overclock it a bit, so to say. The VFD is controlled from Linux CNC. So the speed and start and stop and direction back and forth, that comes from Linux CNC, so there is no manual intervention on this one. Here is an encoder for the spindle speed. You can see that small belt there. So I bought this one. I tried with some homemade stuff there, but this one was much better. It has a very good resolution here, 1000 steps per revolution. It's way overkill, it's not needed, but this one is very useful. It lets me do 2 things really. One is the threading and synchronized tapping, and the other thing is I can have a constant feed rate, so the spindle speed will vary to keep a constant surface speed. Turner also has a gearbox with 6 positions, 6 speeds. I made a cheat sheet, otherwise I will not remember it. But I typically go up to the 4th gear here and overclock that, so I can go up to 2500 RPM. It should be possible to go over 5000, but I'm not sure how wise that is. I have a quick change tool post holder on it, and that is very useful. And this is the 100 size, or this is the 100 size, and I think that is about right size for this one. About the tools here, I only use carbide tools. With inserts here. I just checked my tools and I don't have any high-speed steel tools for the cutting action. The closest I can get that is the knurling tool, but that also means that I have to keep up the speed a bit. I was thinking I can show you how I do when I do some turning here. Here's just a piece of scrap I had, and let's just say I want to turn down to 12 millimeter for a distance here of 10 millimeter, and I want to face off this surface. So this is how I go about to do that, and this is what the screen looks like after a fresh restart. The emergency stop is triggered and I release that one, start the machine, and 0 in on the X and Z axis. That's it. They don't move in any direction. I don't use the 0 function like that. And the first thing I need to do that is to set approximate the right values for the D and the Z parameters. And to do that I need to jog to approximately the right position. So I do that here, and I know that the outer diameter is 20, and I want the end of the workpiece to be at Z0. There, I think it's okay. So I go over here to set 20, and Z should be 0, but 0.5 is also good. There, good. Now I go to cycles, and I have the setting right here, 10 millimeters, and I want to do a test cut now of 1 millimeter, so I'm aiming for 19 millimeter, and now that is precise. I can measure that afterwards and set the correct diameter. So I play the press button. I press the play button here. So 2 passes were needed for that. I just do up a spring pass. and I measure the exact diameter, 18.82. So let's set that. X 18.82. Okay, so I'm good to go for the diameter 12, you can say then. So I do the diameter first and facing afterwards. Okay, so let's just press play. And a spring cut. And measure and end up at 12.03, so 300ths of a millimeter off. Pretty good, but this is typically this machine, it doesn't do exactly. I can do a spring cut. No, they didn't take anything there. So if I want to go down now exactly to this, I will. The easiest thing now is to enter 11.97 and press play. And let's see how far we came with that. I think close enough. 8 micrometers. Okay, that's good. And then I want to do the facing off here. So 12 millimeter, then I jog just slightly outside. There is fine. Then, oops, I need to extend. It dropped here a bit. Then I need to go over to the facing, and I want it to end at 0, and it should be 0 in the middle. 0.1 is alright. Half a millimeter and surface speed is 80, so that is a bit too much for demonstration purposes. 80. Yeah, good. Play. Yeah, there it is. I don't have a good way to show you, but I can promise you that this dimension here is very close to 10 millimeters, and the 12 millimeters is so. Yeah, so that is how I usually do it. And if we want to turn a more advanced shape, I usually model that in Fusion 360 and use the post processor there and download that. Let's have a look. So what I do, I go into the NC mode, the automatic mode, and I select a file, and it's very important to have descriptive names. So 1.ngc is good. Here we have it. Because the tool is now set up fine, it should be just to run. Let's go. as an example, here is a collection of cutting tools I have. This is the one I've used in this video. This is a VNMG insert, and I have a left and I have a right version of that. I also use this CNMG a lot, more for rough cutting, but also when I don't need to have such delicate access. This one is very good to come very close to the live center, for example. Here are two examples of boring tools, one large and one smaller diameter boom. And I would say then the larger diameter the better it is. This one is prone to vibration and shatter. And also here I use CNMG inserts. Another one that is a parting tool. It's of this type. I think parting is difficult. It doesn't work too well for me, I must say. But here you have so far seen 8 tool holders, and it is true you can never have too many of these. At least one for every tool. I do have some more of those booms in the drawer over here. That I take out when I need them. I have, for example, for grooving and for internal threading, and also some other diameters here for boring. Another tool is this one for external threading, and that works good. And I also have for internal threading. And I also have a smaller version of this insert here. This insert here is supposed to cover all the thread pitches between 0.5 millimeter up to 3 millimeters. So it's kind of a universal. It's fine. Here is a knurling tool, and I have some other pattern wheel for it. It works so-so, I would say. In aluminium it works fine. On steel it needs to be such a big pressure that it barely can press in a pattern on the steel. And a chuck, and this is how I do the drilling. I do that by using the chuck in the tool post holder. When I need to turn very big workpieces, and I need to be out here somewhere, I have this holder that brings me backwards a bit. What you see there, that is alternative positions for the center screw for the tool post holder. So if I want to have the tool post further out, 5 centimeter and even 10 centimeter, I can put the center screw in one of those holes, and that works fine. So that will give me a possibility to reach out even that far out. So mostly the operation has been semi-manual or automatic, maybe half automatic. And I will show you a real manual operation, and that is typically when I drill, or at least when I start to drill. But to do that, so I do the drilling using this chuck in the tool post, and it is important then to verify that everything is straight, and it is, you see here, yeah, that is good enough, so I can continue. So the first thing I need to do is to find the center here, because when I know the center, everything is fine and I can do everything. And I will start now. I will not go crazy fast, but I will go pretty fast, 1000 RPM. And now I have established the center position for the drill. Now I can do anything with drilling. And I set X to 0 then, but you have seen that before. So, and just for this video I will just draw through here, and that could be, what could it be, 20 millimeter, 25, let's say 25 minus. And let's do a bit of peck drilling here, that is always nice to have. Yeah, I'll put my hearing protection on and let's go. I try to have some lubrication when I'm drilling, but that went fine. That is typical drilling. Of all operations, I think parting is the most difficult. It seldom works fine for me, but for this video I will make a test. I don't know really where to start, but I go with 500 RPM and let's see where we end up. It worked fine for a while and then it broke. That is typically what happens for me. Anyway, I give up that. Turner has a small party trick it wants to show. Drum roll, here we go. It was neat. This was Turner's party trick, and that is to turn here in a hardened roller bearing roller. Rockwell between 55 and 65 somewhere. It is not a trick, this it is really hardened steel, and I used here a ceramic insert. It's a tung alloy LX11 and that works really fine. And you saw it glowing there, and that is part of it because it is glowing so much that it is dehardened. If that's the right word. It unhardens itself and then it cuts away. So, I mean, all these chips here, it's not a problem. This is unhardened steel, so they can be anywhere. It doesn't matter if they come on the slide race or anything. And here are the chips from this exercise. Steel wool, kind of. The surface finish is above anything really. It is really nice, and so even turning hardened steel, that works fine, even on this small lathe here. I use the live center here as an extra support because it doesn't clamp so good with that hardened steel in the shock here. Anyway, I hope you enjoyed it. I think that completes the walk around my lathe here, and thanks for watching.